Hello there. For this recitation, I have to warn you, there will be some calculus. I know it's scary, but I went ahead and reviewed the entirety of calculus before this video so that I can relay some of my understanding onto you. Show to the power of n is big O 3 to the power of n. Okay, so I think it's easiest to visualize this. Let's say we have some graph. On our x-axis, we have the amount of data we're inputting into our algorithm, and the y-axis is the amount of time it takes for the algorithm to run. Maybe this line represents 2 to the power of n, which is equal, let's say, to some function f of n. This line represents c times 3 to the power of n, and we'll set it to something like g of n. We're essentially saying that 2 to the power of n will never exceed the growth rate of c times 3 to the power of n. And this is true whether c is 1 or c is 2 or anything like that. So there's no value you can plug in for c for which this function will grow slower, will not exceed 2 to the power of n, right? So therefore, we can see visually that f of n is big O g of n, because g of n acts as an upper bound of f of n, which also means that f of n at no point exceeds the growth rate of g of n. So our solution to this problem would be 2 to the power of n is less than 3 to the power of n, right? It must be so, because the base 3 to the power of n is higher than the base of this power here, when n is greater than 0, right? Because our algorithm goes up in terms of how much data we input. We don't input negative data into an algorithm. And we can see that because g of n always exceeds f of n, it is true that k is equal to 0, which is the point when this has already exceeded f of n. Therefore, our witness, the amount of data we input into our function at the point at which g of n begins to exceed the growth rate of f of n, is 0. So 2 to the power of n is big O 3 to the power of n, with c equal to 1 and k equal to 0. C is equal to 1 because this is the constant we multiply against 3 to the power of n, at which point 3 to the power of n will already exceed 2 to the power of n. 3 to the power of n is not big O 2 to the power of n. Alright, so for this one, let's set up a proof by contradiction. Suppose instead that 3 to the power of n is in fact less than some constant times 2 to the power of n. We'll do the algebra. We get 3 over 2 to the power of n, which is less than c. We got this equation by simply dividing both sides of this inequality by 2 to the power of n. Okay. From here, we see that 3 over 2 to the power of n is unbounded. Therefore, it is true that 3 to the power of n is not big O 2 to the power of n. This is our contradiction here, right? Because this inequality is impossible. If we draw this on a graph, we see that 3 over 2 to the power of n grows very quickly. It gets infinitely high, and that's because the base of this power is a value greater than 1. 3 over 2 is 1.5. So no matter what value we put into our graph for c, which is some constant, let's say c is defined here. 3 over 2 to the power of n, at some point of n, will exceed whatever constant we've defined for c. So even if we set c to something like 3 trillion, we set c up really high, there would exist some value for n on this function that causes it to exceed the constant c. So that's what we mean by saying that 3 over 2 to the power of n is unbounded. Its growth rate cannot be bounded by a constant. And because of that, 3 to the power of n is not big O 2 to the power of n. Right, so this problem again has two parts. Determine whether 2 to the power of n is big O, or determine whether 2 to the power of n plus 1 is big O 2 to the power of n. So we have this equation here, and we know that this is simply equal to 2 times 2 to the power of n. We take this 1, this power here, bring it in front of the base and multiply it against the base. So we take this 1, bring it over and multiply by 2, so we get 2 times 2 to the power of n. And we've seen this format before. This could be like a c, and this is just our function. So we have c times some function, which is the definition of what big O is. So we can say that 2 to the power of n plus 1 is big O 2 to the power of n when c is equal to 2 and k is equal to 0 as our witnesses. Determine whether 2 to the power of 2n is big O 2 to the power of n. I have an intuition that this is not true, so let's set up a proof by contradiction. Suppose instead that 2 to the power of 2n is less than or equal to c times 2 to the power of n. Well, then we divide both sides by 2 to the power of n. We get 2 to the power of n is less than or equal to c. But this is, again, absurd, right? 2 to the power of n is unbounded. Therefore, 2 to the power of 2n is not big O of 2 to the power of n. Arrange by big O. So we arrange by the growth rate of each of these functions. And obviously, all right, so I think that if we don't know already, log of n is a very slowly growing function. So even though it's multiplied by 1,000, that constant, that witness c, doesn't really matter in the grand scheme of things, because at some value n, that constant becomes meaningless, and it simply grows at the rate of log of n. So we say that log of n times 1,000 is the slowest growing function. From there, we have square root of n times log of n squared divided by 1 million. Again, that constant, that division by a million, does not matter. It's just n squared. And n squared is much more quickly growing than all the previous ones. Then we have 2 to the power of n, 3 to the power of n, and finally, 2 times n factorial. If you wrote a function that was 2 times n factorial, you would probably get fired. All right, so now we need to use the limit method to show that x squared is big O x cubed. So to do this, we take the limit from x to infinity of whatever we're comparing on the top, and on the bottom, whatever's in the big O notation. So x squared all over x cubed. We do the algebra, we get the limit x to infinity of 1 over x. And then, well, we can't simplify this any further. We know that 1 over x, with the limit to infinity, is just equal to 0. Because it's equal to 0, then it must be true that x squared is big O x cubed. Part B, x log x is big O x squared. We know that this is true just intuitively because we know x log x is more slowly growing than x squared. So we have the limit from x to infinity. We take x log of x and divide it by x squared. This is just equal to the limit from x to infinity. We divide the x's out, we get log of x all over x. So at this point, we have to use some calculus. So we take the derivative of this step, and what do we get? We know that we can reduce this by taking the derivative of the numerator as well as the denominator separately. So what is the derivative of log of x? But it's 1 over x. Okay, and the derivative of x would be, of course, simply 1. Of course, this simplifies further. We get the limit of x going to infinity of 1 over x. We know that the limit from x to infinity, 1 over x, simply gets infinitely close to the value of 0. Therefore, b holds true. Okay, we show that x squared is big O 2 to the power of x. Well, we set up the limit. This is x to infinity, not to 8. We have x squared all over 2 to the power of x. Now, of course, we take the derivative of x squared, and we take the derivative of 2 to the power of x. So we're going to have to apply the limit rule, and this is going to require calculus. So this is just equal to the limit as x goes to infinity. Again, that's an infinity symbol. X to infinity of 2x all over natural log of 2 times 2 to the power of x. This is equal to the limit of x to infinity. Again, we apply the same limit rule because we're not done yet. We have to simplify this further. We take the derivative of 2x, and we also take the derivative of the natural log of 2 times 2 to the power of x. And we get 2 all over natural log of 2 times the natural log of 2 times 2 to the power of x. And of course, from there, it's simple. We see that we have some constant divided by, again, another constant right here times 2 to the power of x. This is just going to become 0 when we apply the limit. And so, therefore, x squared is big O 2 to the power of x. All right, we have the following now. Show that x squared plus x plus 1 is not big O of x squared. We can do this by showing that this limit does not get to 0. So we set up the limit. We know this is just the same as limit x to infinity of x squared over x squared plus x over x squared plus 1 over x squared. This just simplifies to 1. And we get 1 plus the limit x to infinity of x over x squared plus the limit as x goes to infinity of 1 over x squared. We simply split this into multiple parts. Now, of course, the limit of this portion of the solution simply goes down to 0, right? Because infinity divided by a faster growing infinity just gets us 0. This infinity goes to 0 as well. And we're left with 1 plus 0 plus 0, which is simply 1. And because the solution is 1, it is a constant rather than, or it is a constant other than 0. That shows that x squared plus x plus 1 is not big O of x squared. So what is the big O time complexity, that is the worst case complexity of this algorithm here? Well, the worst time complexity is simply the number of loops in this for loop iteration that we need to do. And that would be n minus 1 number of loops. But we simply say, remember we get rid of constants when we're talking about big O. We simply say that the worst time complexity is big O of n. That's because the number of comparisons we make in this algorithm, that is the number of comparisons for this if statement here, is totally bounded by the number of iterations of this for loop. And the number of iterations of that for loop is based on the number n. So even though it's n plus 1, it's based on n. So we say that the big O is big O of n. Okay, so for this one, remember this algorithm was used to, it finds the first term of a sequence of positive integers that is less than the immediately preceding term of the sequence. But, that doesn't really matter. All that matters is the big O notation. And at the worst, we will have to perform n number of iterations of this while loop. So, big O is the algorithm for the palindrome, which I will recreate using the power of video editing. You will notice has big O of n iterations. Remember that it's based on the worst case scenario. So, at the worst case scenario, our loop completes itself. So it goes through n over 2 floor number of iterations. It checks R against R, A against A, C against C, and then ceases. And that's based on n, because we ignore constants. We ignore the division by 2, which is a constant. We ignore the floor function. So that's why it's big O of n. Now, it is true that the best case scenario of this algorithm will be that our string is not a palindrome. For example, we have race call here. This R will check this L, and it will immediately cease the function because there's no need to check that, depending on how you write the function, there's no need to check any more characters. It's not a palindrome, so we return false. Despite this being the best case scenario, it is still big O of n, because at the worst case, we have to perform a check on all of the characters, or at least the first half of the characters, and that's based on n.